Hello. In the previous video, we have defined the quantity known as Joule Thomson coefficient as the rate of change of temperature of a gas with respect to the change in pressure at constant enthalpy, and we obtained the equation for Joule Thomson coefficient mu equal to dou T over dou P at constant H equal to 1 by Cp times T into dou V by dou T at a constant pressure minus V, where the symbols have their usual meanings. So this is where we have stopped in the previous session. Now let's continue. So let me call this one as some equation 4 or something like that, or you give some continuous number for that. Now we will elaborate on this quantity, and we'll see how this quantity helps us to predict the nature of temperature change for each gas. Now we can express this mu in terms of yet another important quantity, which is known as the volume expansivity of a gas. The volume expansivity of a gas, is represented or given by beta. We already used this one in our previous discussions. 1 by V, beta equal to 1 by V times dou V by dou T at constant pressure. You can understand that why we are referring to this quantity, because already you can see this dou V by dou T to P in our equation number 4. So we are trying to just simplify that equation in terms of beta. That is what you're going to see, right? So this is the expression for volume expansivity of the gas. So from this particular thing, can you get an expression for dou V by dou T to P? That will be equal to beta V, right? Therefore dou V by dou T at P, that will be simply written as beta times V, right? Beta is an experimentally measurable quantity and V is also an experimentally accessible quantity, so beta V. So let me call this one as equation number 5, and let me substitute this equation in 4. So what will be, therefore substituting 5 in 4, what you will be getting? You will be getting mu is equal to, now you can just write simply equal to as mu, that's enough. You know it is dou T by dou P at H. Mu is equal to simply, that is 1 by, right? Yeah, it is beta V, 1 by Cp, right? 1 by Cp times T into, right? T into beta V, right? T into beta V minus V. So what you can do here, you know, it's clear that V is once again a constant, a common term over here. So I can take V outside, so it will be finally becoming V divided by Cp. What is in the bracket? What is remaining in the bracket? That is simply T beta or beta T, I can write. So beta into T minus 1. Now can you see that the equation has got simplified further? So that, let me call this one as equation number 6. It's up to us to recall any form of the equation, right? Now with the same modification, or with the same modification, we had a previous equation. So I take your attention to this equation. We had some equation like dt equal to, before we defined mu, we had an equation for dt. Okay, so let me take you back to that equation. In our previous slide we had it. So you look at this equation, yeah, see where we had it. Yes, of course, here you had it. Okay, let me give some number for this one. So let me call this one some 3a or something like that. See, can't you see that here? What is that? Cp dt is equal to, right? So this one was your equation, Cp dt equal to. From that you could have written what is dt equal to. What will be dt equal to? Dt equal to 1 by Cp over T dou V by dou Pt. So dou V by dou T at P minus V into dP, right? So here for this particular dou V by dou T at P only, we have substituted as beta V. Okay, so I can rewrite this equation 3a as dt equal to the same thing. All other things are remaining because we have just used the same thing. So you can just try it out, you can verify it. So I'm writing equation 3a. Equation 3a can be modified as dt equal to, because we are interested in how much will be the change in temperature for the system. That is why we are writing this one. Okay, so dt is equal to, I can write dt is equal to V by Cp, into, see, this is the same thing only, beta T minus 1 into dP. Okay, so that is my 7th equation. And see, you can just clearly understand, even if you do not go to 3a, you can use the definition of mu. Okay, so that also is another method. That is because what is mu? Mu is basically equal to what? Dou T over dou P, right? Dou T over dou P at constant H. Since it's already constant H, you can take it as equal to what? Simply dP by dt by, you take it like this for the time being. Already constant enthalpy has been used, dt by dP. So in that case, you can write dt equal to mu into dP, right? Mu into dP, and for mu you substituted this equation number 6, V by Cp. So that is the way in which you got V by Cp into beta T minus 1 into P. And this is the fundamental equation of Joule Thomson effect actually. So this particular equation I want you all to remember, so as the fundamental equation representing the Joule Thomson effect, because that gives you how much will be the change in the temperature. Okay, you can use this quantity to define mu also. That's all up to you. It can be V by Cp into, or this equation also can be used. This particular equation number 6 and 7 both are relevant, right? See, now it gives the temperature change in temperature due to Joule Kelvin or Joule Thomson effect, right? That be useful for doing problems, and that's why I mentioned it as the fundamental equation. Try to recall it or memorize it, okay, so if possible. Now let us discuss one or two cases and finalize this or conclude this session. So you can see in this equation dP here dP, what is dP? dP is equal to change in pressure, right? So that is nothing but Pf minus Pi in our throttling process. And hope you remember that we assumed that we are in the particular phenomenon, the gas is undergoing an expansion from initial high pressure to final low pressure. Is it not? Initial pressure Pi to a constant final pressure Pf. So Pf is lesser than Pi. So what about the sign of dP, which is Pf minus Pi? So you can see that dP will be negative. So that is something very, very important that you have to remember in throttling process. In throttling process, the dP will be negative. Okay, or it represents what is known as the fall in pressure. dP represents the fall in pressure. How much the pressure will be reduced? Okay, fall in pressure. Whereas all other quantities in equation number 7, right? dP is negative, beta is positive for the gas, temperature is always positive, volume is positive. So Cp, it's a positive quantity. So all other quantities are positive, right? So let's and other quantities. There's something notable. That's why I'm just writing quantities in 7 are positive. So have this idea in mind. Now with this idea in mind, we will discuss several cases, 3 cases okay, specifically. So case 1, if the quantity in the bracket, we have to predict whether there will be an increase in temperature for the gas or decrease in temperature of the gas as a result of Joule Thomson effect. Okay, so if beta T, is it not, beta T minus 1, if beta T minus 1, that is a quantity which will decide the sign of dt now. dp is already negative. Okay, if beta T minus 1 is positive means what? It is greater than 0. If beta T minus 1 is greater than 0, it's positive. Or what does it mean? Or I can write, if beta T is greater than 1. Okay, so if this is positive, then dt will be negative. Is it not? dt will be negative. Why dt will be negative? Because dp is already negative. So dp is already negative. This quantity, we assume that it is what? Positive. So dt must be negative. Okay, clear? Because v and cp are always positive. So then what's the conclusion? dt must be negative. dt is negative. Okay, and what is by dt negative? It means that, what is dt? It's always t final minus t initial. Always dt changes in any quantity dx, it should be final minus initial. That is our meaning. Okay, tf minus ti is what? Negative, right? It's negative means it's less than 0. Or what does it conclude? It concludes that tf will be less than ti. And what is the meaning? Tf less than ti means what? The final temperature will be less than the initial temperature. So in those cases, there will be a cooling effect. Cooling occurs for the sample, given sample. Cooling occurs. So you can see that whether or not a particular sample of gas will be cooled or getting hotter, it depends on beta T. Beta is nothing but what? The volume expansivity of the gas. Okay, defined by this particular equation. It is different for different gases, volume expansivity, and also it depends on the temperature at which the gas is trying to be cooled. Okay, that is why I mentioned in the introductory session that the extent of cooling will depend upon mainly 3 factors. One is the nature of the gas. Second one, nature of the gas means the value of beta will be different. Second one is the initial temperature. Okay, at what temperature the gas is undergoing throttling process initially, right? Okay, so if the temperature is suitable, so that it beta T is greater than 1, then there will be a cooling effect. So if the beta T is not greater than 1, then we'll see what will happen. If it is less than 1, of course there will be a heating effect. We'll see. So the second one, case 2. So that is okay. You just try to the introductory lecture. So case 2, if beta T minus 1, this factor, if it so happens that this is equal to 0, what does it mean? It can happen, of course. Okay, at some particular temperature it can happen, or for some particular gas it can happen. Okay, beta T minus 1 is equal to 0, or beta T for that particular sample is equal to 1. Then automatically you can see that equation 7 says that dt will be equal to 0. It means that there is no or neither heating nor cooling, no Joule Thomson effect. I can say like that, no Joule Thomson effect in that case. Means neither cooling effect nor heating effect will be there, right? Then case number 3, if simply it's the opposite of case number 1. If beta T minus 1 is less than 0 or beta T is less than 1, right? So you will see that in this case dt will be obtained as positive. Dt is positive. right? Or it means that TF will be greater than Ti, and that's an interesting thing. TF is greater than Ti. Okay, the gas sample will not be getting cooled. Instead, what will happen? It can get heated up. Actually, this one was observed in the initial experiments and all, and actually this led finally to think of that won't there be some sort of molecular forces. Okay, so we had the assumption of perfect gases, and this particular Joule Thomson effect has proved that there is some sort of intermolecular forces that is existing, and that concludes that a given sample of gas may either undergo heating effect or cooling effect, okay, depending on the number of factors like its initial temperature, okay, or the very nature of the gas itself. In some cases there will be a heating effect, in some cases there will be cooling effect, and in some cases there will not be any effect at all. Okay, and we mentioned that for ideal gases in the introductory lecture, we mentioned the ideal gases do not show Joule Thomson effect, even though it shows what? The Joule effect. Okay, we'll discuss the Joule Thomson coefficient for ideal gas and the real gases in the next session, maybe on the next day. Okay, thank you.